Last time we looked at the idea of a partial derivative for a function of two variables, and we saw that this is pretty much the same as a regular derivative, except that we have to distinguish which variable we're taking the derivative with respect of and which variable we're actually considering as a constant. Well, we can continue that game just like we did with the regular derivatives and bring it into the idea of higher derivatives. Okay, so what we can do is we can consider higher order partial derivatives for a function of two variables. So for instance, if we think of this function as a function of x, we have our good old idea of the second derivative, that being the derivative of the first derivative, and we can do exactly the same thing for this function. The only thing that changes, as you notice, is the notation. Instead of the d, we're going to use del because we're talking about partial derivatives. But in terms of computations, nothing changes. It's still the same rules that apply. Or we can do it in terms of y, and again, same notation. We have a second derivative once we think of that as a function of y, and if we want to emphasize that we're coming from a function of several variables or two variables, then we use the del notation. So far, so good. Absolutely nothing new. But what is new is that we can also make things up. What do I mean by that? Well, what I can do is I can consider the second derivative of a two-variable function with respect once to x and once to y. So it'll be the second derivative of x with respect to x and y. Notice one thing, however, about the order in which I write this. If I write second derivative of f del x del y, that means I'm first computing the derivative with respect to y, that is the derivative on the right hand side, and then the one on the left hand side. This is nothing new in mathematics. Whenever we're dealing with functions and we're doing compositions and so on, we're always applying things from the right to the left. But again, it's just something for you to consider. By the way, in a few minutes you'll see something that is going to make our life a lot easier in terms of the order differentiation. Now, of course, if we do it in one order, we can also do it in the other order. So we can take the derivative of the function with respect to x first, and then with respect to y. So these are, for obvious reasons, called the mixed second partials, or the mixed second partial derivatives. And of course, we can, just like we've done for regular functions, we can keep going and we can go to the third derivative and the fourth derivative and so on. And there is all kinds of different combinations in there of which order we can actually do our derivatives, or 3 or 4 or whatever many derivatives we're doing, if we're using mixed partials. And again, as I said, there is something quite important about that order of differentiation. So the important thing about these mixed partial derivatives is the following property, namely that the order in which we take a mixed second partial derivative does not matter, but as long as the second derivative is continuous. So once we compute this mixed second partial derivative, if it turns out to be a continuous function, then it doesn't matter which order we're going to take that those two derivatives, the result is actually the same. So in other words, the order of differentiation can be switched if this continuity exists. So this means that a lot of issues having to do with the order in which we take the derivatives may become irrelevant as long as we have continuity. Again, at this stage, that's always going to happen, and we're not going to look at special cases, but next year that might change. And so this is basically all you need to know about higher order derivatives, and this is the only really important property that you need to know. So we're going to move on to something else then.